All right, this section of the midterm review is going to be on the effectiveness rankings. They get their own section. That's how important they are. This is, again, from that paper, Graphical Perception. Again, not opinion-based. This is experimental. They asked thousands and thousands of people, how much bigger is this circle than that circle? And if this color equals 50, what color does that, what value does that color represent? And, then they just figured out which methods of encoding data are the easiest for people to extract, precise values from. It's about accuracy, right? This doesn't mean that the things that are the low down on the effectiveness rankings are bad. It's about being able to accurately pull values from a plot. So this is kind of the money image that came from their research. It's a visual legend showing the rankings and the encoding types. At the top are the methods of encoding data that humans can accurately assess. The ones at the bottom are better for showing trends and generalizations. So again, this is important because if the point of your plot, or if there are certain parts of your plot that you want humans, your readers, to be able to extract values from correctly, accurately, you're going to want to make sure you're encoding those pieces with techniques from the high end of the accuracy ranking list. Okay, so let's just run through these again. Position along a common scale is the most effective for being able to accurately decode values. And this is a great example. We've got 2 common scales, and it's easy for humans to be able to make these comparisons. Okay, and then the second most accurate is position along an identical but unaligned scales. So these kind of small multiple plots. Length is the third most accurate. This ridiculous plot, but I didn't change it. In pie charts, a good example of angle and slope. These are the fourth most accurate. We also see these in line plots, time series plots. That's where we're comparing angle and slope. Slope plots like this. It's right in there. You can probably understand these numbers here probably mean more to you than actually looking at the slope. The slopes give us a general idea, increase, decrease, and how much is it increasing. It's decreasing more than it's increasing in this case, right? The blue line versus the red line. So those are the things that we can detect, but it would be really hard for you to say this is an increase of 12%, where this is a decrease of 49%. I'm just making those numbers up. What we get is a general sense. Area, like we just talked about, area is kind of commonly underestimated by humans. It's everywhere. It's, in a tree plot like this. It's in proportional symbol plots. We use area to encode all sorts of things, but again, that's not the way you want to hand it to your audience if you want them to be able to say this, geckos are 47% of reptiles, whatever it is. They're just a lot. They're a lot. Volume, density, color, saturation. These are low down on the ability to say, oh, this shade of green equals 13 and this one equals 22. That just doesn't happen. And whatever the scale is here, we can just tell that one is more than or less than the other. And then, color. Color is just there to show us patterns and give us an intuitive sense of things, in my humble opinion. So again, this is for comparing numerical quantities accurately. We use all of these methods all the time. Just know that the ones that are the most accurate for pulling true values from are going to be at the top of this list. And then just as a reminder, line charts don't need a zero baseline because we're comparing the angle, just like time series pie charts. You don't have to have a zero baseline. It's only for bar charts. Okay.